So say that one more time. So you said delta G equals.
Gas constant times temperature times the natural log of QC, or I guess the Q whatever, over K.
Excellent. So now we can use that relationship. Oh, no negative though. Sorry. And so now we can compare, right? So compare our Q snapshot to our K. So let's go ahead and do that. So what's Q then for this scenario? Thank you. So what's Q? Yeah, let's walk through it. So, right, let's just set up our K equilibrium. Well, that's hydronium times nitrite over nitrous. Right, so that's our Q. So then we just need to plug in our molarity values. And so I had skipped ahead mentally. And so we can plug them in. So if they're all equal to each other and they're all 1 molar, right, we just have 1 times 1 over 1. So now our Q is 1 in this case. And so now we can plug in, so RT over ln, so 1 over our equilibrium constant. And so what do we get for that? So would it be spontaneous? So no. So under these conditions, right, not spontaneous. So we're saying, right, it will not dissociate. So equal to 18 kilojoules approximately, which was basically what we had kind of seen up there. So that made sense with our Q of 1, plugging that in. Yeah, because, well, this is just the standard conditions, right, at equilibrium. So now it's saying if it's at equilibrium, right, it's not going. But then we calculated our delta G. And then, yeah, so now we calculated under new conditions with Q. And so now we're just saying, okay, once they're 1 molarity as well, right, nothing's going to happen. Well, they're all identical, and then they're all kind of large, right? So we can, without doing any math, so just thinking, okay, let's look at our equilibrium constant. It's 10 to the negative fourth, right? But we have 1 molarity of concentration of everything. So just kind of thinking through it, it's like, well, maybe I wouldn't expect it to go, because that is pretty small, and there's already apparently 1 molarity existing. So just kind of thinking through it logically, I wouldn't expect it to go. But then, right, yeah, then we just plug it in with the math. Okay, let's see how that compares with our Q value compared to our K value. And we could even think back to, before we got into all this delta G stuff, we could just say, well, our Q is 1, but our K is 10 to the negative fourth, so it's already past where it is in equilibrium value. So that kind of gives us a hint, but yeah, then the delta G just verifies that for us.
And to mathematically sort of relate the two, those two expressions that we have, because Q is 1, they're exactly the same, because that's just K to the negative 1, and with logarithms, when the argument is to an exponent, you can take that argument in front. And so that would just be saying basically the same thing.
So now with that, let's check out the next set of conditions, because this one is kind of more difficult to tell. So before, right, we even attempt the math. So now let's look at the second condition. Well, it's saying our nitrite and our hydronium concentration, so they're pretty small. So they're on this order of 10 to the negative fifth. We're at 10 to the negative fourth in our Ka, so hard to guess. And then we still have 1 molar of our starting material. So just guessing, it's harder to tell. It's like, well, maybe it will proceed forward. That seems kind of like it might happen. So let's do the math and verify that. So see if you can figure that out. Do people need some time to do that?
So was that 10 to the negative 3 or negative 5?
-5. Zoom in. So let. Oh my gosh, what is going on? So I'll just start going through it. If I could draw. So we can plug in and solve for our Q snapshot again. So we had our 2 dissociated ions were 10 to the negative fifth, and then we had over 1. So I'm just plugging it in right to our Ka up there, over 1. And then we should get something pretty small. Yeah, so that's our Q now. And so we could kind of stop here and just kind of think through it. Well, now we've verified that our Q is less than our equilibrium constant. So I would expect it to go forward, but let's plug it in to our delta G and verify that. So we can use our same equation. So RT times our natural log of Q. So 1 times 10 to the negative 10 over the 5.6 times 10 to the negative 4th. Times our temperature, and I assume we're still at 298, times our gas constant. And so now we have a negative delta G, so I'll round it to equals negative 38.5 kilojoules roughly. And so now we can say, yes, it is spontaneous, which again matches what we kind of thought. No, it should be negative. Well, if we expect it to be negative if it's spontaneous, and yeah, that's what I got. Because remember, there's no negative sign there, and then you do the natural log of this, and I got negative 15. Questions about that one? All right, let's try another one. So similar. Now we're relating our solubility product constant. This one is negative 10. Here, I'll zoom in. How's this one coming along? Do we have our delta G for this reaction? So what formula should we use?
It would be delta G equals the negative exponential log of KSP.
Excellent. So we can still use, right, the same equation. So it applies to any equilibrium situation. And then what did y'all get for our delta G then?
Like 55,000.
55,000. Or I'll change it to about 55 kilojoules. And so this is similar to the math situation that we saw before, right? So we could kind of think through this. And so then it asks, is it possible to prepare solution that is 1 molar in both silver plus and chloride? And so, right, just kind of think through it. Well, if your KSP is silver times chloride concentration, but then it's trying to make a 1 molar, so that's 1 again, kind of like how we saw. And so now we can see that we're basically going to spit back out, right, our delta G that we calculated at equilibrium. So basically we're saying, no, we can't, since it's just too large of a concentration compared to our KSP. And I can plug this in, so right now we have our Q, and then we can plug it into our delta G equals RT over natural log, what was it, Q over K, right? Q over K, which gives us back to RT times natural log of 1 over our 1.8 times 10 to the negative 10, so our KSP. So that gives you the same answer, so 55 again. So not possible. Does that make sense for that problem?
I don't know what the units were for the R again.
R is, because it's 8.314, so joules, moles, Kelvin.
Okay.
So yeah, it scales with the moles and then, of course, temperature.
Okay. That was kind of confusing me because I know that there was also, I think, the gas law constant, and so for some reason I was thinking that it had to do.
Well, it's similar because it depends, because it's the same gas law constant. It's just whether you're dealing with units of energy or moles, like we saw with the PV equals nRT. That's a different gas constant.
Okay.
Yeah, because it
still works with aqueous solutions.
yeah, because it's like an energy thing.
Okay.
All right, let's try this next one. Once I zoom in on it. And so if you don't have your textbook, you can just ask the internet for the appropriate values. It wants you to calculate the delta H of the reaction and then calculate our Kp at a different temperature. So just a reminder, your book does have pretty helpful like equations at the end of every chapter. So I'm looking at page 888 in your textbook or chapter 23, because that's just a nice summary of all the ones that you were given in lecture, because you might need some of them, especially the ones at the bottom for this problem, the Van Hoff, and later we'll need that Clausius equation that I've given as well. So just keep that in mind. So let's start walking through this one. And so let's just write off their heat of formation, so standard heat of formation values. So what do we get for PCl5? What do we find? Any? What did you get?
I got negative 374.9.
And that's kilojoules, right?
Yes.
Okay, just checking. And what's chlorine gas? What should it be? 0, yeah, so it's 0. So if you can remember way back, so things that are in their elemental form should have a standard heat of formation of 0. But you could have looked that up and verified that. And then what did you get for PCl3 then for the standard heat of formation?
Negative 287.
Negative 287 kilojoules. And so now let's do that. So find our delta H of our reaction. Luckily, we don't have to multiply anything by their molar amounts, so we can just take, right, our sum. So products minus our reactants. So then we get negative 374.9 minus negative 287. So then, do we get negative 87.9? Did I plug that in correct? Is that what other people got? Okay, just checking. So that's negative 87.9 kilojoules. So that's our change in enthalpy for our reaction. And so then it asks us, so given that our equilibrium constant is 0.55 bars at 250 Celsius, calculate the Kp at 400. So what equation do we need? So you probably have to go back to your notes, so that's where I was suggesting the textbook.
I think that you would be able to use the relationship of natural log of K equals the enthalpy, change in enthalpy over gas constant times 1 over temperature plus entropy. And in this case, because there's not really any change in conditions, entropy just goes to 0. But I'm not sure if that would be the most effective way.
Yeah, I would put it in this form. I'd probably skip to that form. Let's see, which equation are you looking at exactly? Oh, yeah, you're looking at the 23.27 equation.
I don't know. I don't have my book with me, so.
Yeah, that's why. It's just different forms. But this is a better form just because it has the 2 Ks, so it already moved it into the form where we could compare it, as opposed to, yeah, rederiving it from ignoring the change in entropy, which would work, so you probably would have gotten there. But this is just kind of the put together form of that. So this is the Van Hoff equation. And so then we can plug it in, but of course, right, temperature needs to be in Kelvin. And so let's set everything properly too. And so that's the only thing that you don't want to mess up is what your K2 is versus your T2. So I'll set T2 at 400, which is plus 273, so 673 Kelvin. And so we're trying to find K2, so X. We have our K1, which is our KP, so 0.55 bar. And we need our T1, so just need to convert that. So it was, I'm not going to do mental math, so 250 plus 273, so 523. And so we have our delta H. Gotta watch the units though, right? So we calculated this in kilojoules, but what's our R in? Just joules, so we need to put this back into joules, so just watch that. And so now it's just turning into algebra slowly. So equals, so now I'm going to change this to negative 87,900 roughly, 8.314. And then again, our T2 based off of how I set everything is 673. So minus 523 over our two temperatures. And so now just math. So far I got natural log of x over 0.555 is equal to negative 4.505 or 506. So I saw at least one nod. Does that look?
It's a little off for me, but it's around negative 4.5.
Yeah, as long as you're around negative 4.5 or so, because I'm sure we might have different numbers for the energy a little bit potentially, or and so then everything to the E. So now we have x over 0.555 is equal to is 0.01104. And so solve for x. And so I get about this for our new pressure.
Wait, what's the negative sign in the 555, or is that just a point?
This is a negative sign. Wait, so
Oh,
this,
not in the 555, that's just a point.
yeah, that's a point, so 0.555.
My bad.
Yeah, and then just multiply, so get about, yeah, 0.006 for a new KP. So at our new temperature, which was 400 Celsius. Let's see. Let's do 65 at least, because this one, at least I think it should be easy, maybe. So So see if you can determine the signs. What is up with this connection? And for A, you shouldn't have to start looking at values or anything. So just kind of think through what reaction it is. So let's look at A. So what kind of a reaction is A?
That's, I guess, a combustion reaction.
Yeah. So it's a combustion reaction. So that was your biggest hint, right? And so in a combustion reaction, so what's the sign of the heat exchange?
Positive, right?
Negative.
Negative, since, yeah, heat's being released. So delta H is negative. So exothermic reaction feels hot. And what can we say then about our change in entropy? What do you notice? Do you notice anything? So less moles, and right, everything's in the gaseous state. So since it's less moles, right, then our change in entropy is negative as well. What about B? So what kind of a process is going on there? Sublimation. So then what do we need our delta H to be?
Positive.
So positive, so endothermic reaction. And then what can we say about our change in entropy? So sublimation, solid to gas, so what does that do? So think about the states. So positive, right? So that's just from more order to more disordered as you go from solid to gas. So obviously more states that they can be in. And then what about the last one? So now we have 1 liter of helium and 1 liter of argon are allowed to mix. And so is there any heat exchanged in this one? So no, so that was a little tricky. So our delta H is 0, right? So there's nothing is getting hot. They're not changing states, so no heat transfer. But then what about our change in entropy? So positive, right? So more mixing, so more allowable states. So yeah, positive. Good, that was a good one. These are always good candidates for like multiple choice or quick answer problems. So we're kind of running out of time unless you just want to do all the last two. So let's see, what do we have? Our two options, so we can look at the solubility one, and so this kind of relates our K to our delta H again, if you want to look at that. So this is kind of tricky, or we could look at the acetone one, and this is related to the Clausius-Clapeyron equation. Or we could do both if you all are feeling dedicated. How are we feeling?
I'd like to maybe go through both.
Let's try the acetone one first. I think it's a little simpler, and then let's go back and we'll do the solubility one. That one's a little tricky. And so we have acetone is used as a nail polish remover, and it's given its normal boiling point and the enthalpy of vaporization. And so calculate the equilibrium vapor pressure of acetone at 20 degrees Celsius then in torr. And I'll at least highlight this phrase, normal boiling point might be key. So how's this one going? What equations could we use? What other information do we need? So what are some thoughts? What?
Can you give us the initial equation?
So I gave a hint, so it's the Clausius-Clapeyron one. So our natural log of pressure 2 over pressure 1 is equal to our delta H vaporization over R times the T2 minus T1 over T1 times T2. And okay, well, they gave us the enthalpy of vaporization. It's just in kilojoules, so that's fine. And then why did I highlight normal boiling point? What does that mean? You kind of have to think back. What was the definition of normal boiling point?
1 atmosphere.
So 1 atmosphere. So that was the key. So we're at 1 atm, aka right 760 torr. And so now we can basically start plugging in our numbers now. And so we're trying to find, so we just need to set our P2, P1 properly so we don't get confused. Let's see. Since our boiling point is 56, I'm just going to set T2 as a higher one and then just be consistent that way. So let me add 273 to that. So then our T2 is 329.2 Kelvin. So T1, we're trying to find it at 20, so 293 Kelvin. And so we have our P2 then, which was the 760 torr, so we're trying to find our P1. And so now at this point, we're just good to plug everything in and solve. Just don't forget, again, to convert to joules on our change in vaporization. And then again, don't mix up your T2, T1 scenarios.
So our constant, that's 8.317, right?
Yeah, it's still the 8.314.
Oh,
Sorry, I have bad handwriting. Now I'll just do the math at this point. So far I have this, and just double check. So natural log 760 over P1 or X is equal to 1.307. And then we can take everything to the E. And so then I get a new pressure of 205 torr then at that temperature. So pressure at 20 degrees Celsius is 200 torr. Or I guess I should have rounded to 206 for a little more accuracy. Questions about that one? All right, let's try the last one. And I think it'll help for the quiz, because it's a good reminder of the quiz stuff. And so I'll give you some time to look at it before we start talking about it. So it says we have the solubility of potassium iodide is measured as a function of temperature, and you have the data here. So there's our temperature at degrees Celsius at certain increments, and then the solubility. But of course, take a note at those units. That's my first hint of the day. And so see if you can figure out how you might get our delta H values for our dissolution. And so what do we have to do for this one? What are some things we can do? How can we set it up?
Are we gonna wanna convert our grams to liters to like molarity?
Yeah, so that's what I would do. So right in, this is my next hint for the quiz. So watch the units on the quiz because we didn't practice it too much in class. And so right, like we're saying, so solubility, usually when we do our calculation, it's in molarity, right? So your KSP is related to your molarity. But this time we were given our solubility in grams, so yes, we should convert it. So let's do that. So again, watch for that on your quiz. You might have some conversions back and forth. And so what I would do is let's pick two values. It doesn't really matter. We might want to pick the more extreme ones to try to get a bigger difference. So looking at the solubility at 10 and looking at the solubility at 80. And so let's convert them. So we're at 0.058, so grams per liter, but we need moles per liter. So we need to divide by our molecular weight of potassium iodide. Or lead iodide, I don't know why I said potassium. So lead iodide, I think it's 461.01 grams per mole. So divided by that, grams, mole. And so now this is smaller. So now, so 1.258 times 10 to the negative fourth. So our solubility. So again, molarity now. Let's change our units. So moles per liter. And let's do the same with our 80 value. And so that one, and let me just put on the side, so this is at 10 degrees Celsius, so we can remember. And so 0.366, convert again. And so this is just our molar solubility. So 7.939 times 10 to the negative 4.
Where do you get the 461.01 grams?
That was, I think that's the mass of lead iodide. Let's say. Like I stole it from the internet. I could add it by hand if. Okay, just checking. So then we're here, but then our formula, so let's go look at our formula that we're aiming for. So right, we want to put it into our Van Hoff equation. And so our Van Hoff is our natural log of K2 over K1 is equal to, so we're trying to find our delta H of our reaction at these certain temperatures, so we'll plug in our temperatures in a second. But we're still not quite there because we need K, right? Because we have molar solubility. And so we could plug in the formula for K, if you remember that relationship. For me, I'm going to quickly do the kind of the scratch work so I can figure that out. And you might remember the formula too, because all of the ones that disassociate the same, right, they have the same like KSP formula. which we could go back in the formula and derive, but I'll just kind of put that, so those are S plus 2S, right? Plug that into our KSP, and we get, so 2S squared times S, so that's how we get that 4S cubed. So does that kind of look familiar to people with our formula? And so that just means that we need to plug this value in to here. So we could either solve for our K's, so maybe that's easier. So let's find our KSP then at this temperature. So I'm just going to plug that value in cubed. So 1.258 times 10 to the negative fourth, cubed times 4. So there's our 1K, so 7.96 times 10 to the negative 12. And do the same for this one. So cube root times 4 again. And so now we can start to at least appreciate their difference in KSPs. So KSP2 times 10 to the negative 9 at this different temperature. Let me know if those values look okay. Double check me. Okay, and so now that we finally have our K values, we can plug them in to our equation. And again, for my sanity, I just set the 2-1 as the higher value. It doesn't really matter as long as you're consistent. So K2, I'm doing at the higher temperature, so that 2 times 10 to the negative 9 then over our other K value. So 7.96 times 10 to the negative 12. So equals, so solving for delta H of our reaction, 8.314. And then T2, so 80 plus 273. So 353. So now 353 minus, and our other temperature was at 10. So 283. And math. So now we just have to algebra. All right, so I got this for my final answer. And so this is in joules. So about 65.5 or 65.6 kilojoules for our delta H of our reaction. And then, so then it tells us that the actual value is 63.4. So I feel pretty good about our determination there. I got, so 65.6, so plugging that in, right, it comes up to 65,527, and then I just converted it to kilojoules. All right, that was a little long. I'll go ahead and pass out the quiz in case anybody is eager to get going, but otherwise just take your 10-minute break. Again, watch your units. So that should help, so just show your work as well. And then is this field trip sign up thing still kind of